If you stepped onto the surface of Mars right now with no helmet, no suit, nothing but the clothes you're wearing, something would kill you within about 15 seconds. Before we get into what it actually is, I want you to genuinely guess. Most people's first instinct is the cold, since Mars is famously freezing. Some people guess suffocation, gasping for air that isn't there. Drop your honest guess in the comments right now, cold or lack of air, before you keep watching, because I promise you the real answer is neither one, and it's stranger, faster, and considerably more interesting than either guess. If you're the kind of person who wants your assumptions about survival completely rebuilt from scratch by the actual evidence, go ahead and subscribe, because that's exactly what tonight's video is going to do. I want to be upfront about something before we go any further. This isn't going to be one of those videos that teases an answer for 20 minutes and then gives you something disappointing. The real answer is coming, and it's coming with actual numbers, real spacecraft data, and even one genuine human account of almost exactly this scenario happening on Earth. But to actually understand why the answer is what it is, rather than just being told a fact and moving on, we need to build up a little bit of groundwork first. Groundwork that's going to completely change how you think about something you've probably never once considered in your entire life. The actual physical pressure of the air around you right now pressing on your skin. It won't take long, and I promise the payoff is worth the short walk there. It's a strange thing to sit with for a moment. The process that would actually end your life on Mars has nothing exotic about it at all. It's the same basic physics of pressure and gas behavior you could, in principle, demonstrate in a modest lab here on Earth, using nothing more advanced than a vacuum chamber. And yet almost nobody ever connects that ordinary physics to the specific, vivid question of what would actually happen to a person standing on another planet. That gap between physics simple enough to explain to a curious kid and a question most people have never actually worked through carefully is exactly the gap tonight's video exists to close. And closing it properly means resisting the temptation to just hand you the answer up front and move on. Because the answer, without the reasoning behind it, is just another trivia fact, forgotten by tomorrow. The reasoning is what actually sticks. Here's the assumption almost all of us are carrying around, whether we've ever said it out loud or not. We picture Mars as basically a colder, emptier version of a cold desert here on Earth, someplace like Antarctica but with less air. And under that mental model, the story of dying there writes itself the way it would on any brutally cold Earth expedition gone wrong. You'd get cold, then colder, then hypothermia would set in, and eventually your body would shut down. It's a reasonable guess, and it's the kind of guess almost anyone would make if you asked them cold, on the street, without any warning that the actual answer might be something else entirely. It's also almost completely wrong, and figuring out exactly why is going to take us somewhere genuinely strange, into physics that sounds more like a myth than a measurement. Except every single number we're about to walk through has actually been measured, calculated, and confirmed by real spacecraft pointed at a real planet sitting out there in our solar system at this very moment. There's something almost comforting about the way most people imagine dying on Mars, if that's not too strange a thing to say. We picture a slow, cinematic kind of ending, wandering across red dunes, breath fogging, temperature dropping, maybe a dramatic collapse in the sand as the last of your strength gives out. It's the kind of death that unfolds over minutes, maybe longer, with time to reflect, to feel the cold seeping in, to understand what's happening to you. It's worth naming why that cinematic version feels so intuitive to us in the first place. Almost everything we know about extreme cold as a species comes from stories of people surviving or failing to survive brutally cold conditions here on Earth, mountaineers caught in storms, explorers stranded in polar wastes, stories that have shaped centuries of literature and film about what it means to die in a frozen landscape. Mars, visually, looks like exactly that kind of place, a cold, empty, reddish desert, and our brains, quite reasonably, reach for the closest familiar story to make sense of it. The problem is that Mars isn't actually playing by the rules of a cold Earth desert at all. To understand what it's actually playing by the rules of, we have to start with a number most people have never had a single reason to think about: atmospheric pressure. Here on Earth, at sea level, the air around you is pushing on your body with a pressure of about 101,325 pascals. A unit scientists use to measure pressure, or if you prefer a more familiar unit, about 14.7 pounds per square inch. You don't feel this pressure as a crushing weight because your entire body, inside and out, has evolved and adapted to exist in exact balance with it. The air inside your lungs, the fluid in your inner ear, the blood moving through your veins, all of it is calibrated to that specific amount of outside push. To get a feel for how much force that actually represents, consider that the total weight of the air pressing down on an area the size of your outstretched palm is roughly equivalent to a couple of bowling balls resting on that same spot. Scale that up to your entire body's surface area, and the total force involved is genuinely enormous, roughly equivalent to the weight of a small car pressing on you from every direction at once, held in perfect invisible balance by the matching pressure inside your own tissues. You don't feel any of that weight because the pressure inside your body pushes back with exactly the same force, in every direction, all the time. A balance so perfectly maintained since before you were born that you've genuinely never had a reason to notice it. It's only when that balance gets disrupted, suddenly and severely, that the sheer scale of what's normally being held in check becomes obvious. Now, on Mars, the atmosphere is real. It exists. It's not the total vacuum of open space. And that distinction matters more than you'd think. But Mars's atmosphere is astonishingly thin, averaging around 600 pascals, which works out to about 0.6% of the pressure you're experiencing right now, sitting wherever you happen to be. Even in the very deepest low-lying basins on Mars, where the pressure is at its absolute highest anywhere on the planet, it still only reaches around 1,100 pascals, barely over 1% of Earth's. At the top of Mars's tallest volcano, Olympus Mons, a mountain roughly 2.5 times taller than Everest, the pressure drops to as low as 30 pascals, thinner still, low enough that even the ordinary carbon dioxide making up nearly all of Mars's atmosphere would itself start to behave strangely at that altitude and temperature, hovering right at the edge of where it would begin condensing directly into dry ice. Here's a detail worth sitting with before we go further, because it's the kind of everyday clue that's been hiding in plain sight your entire life without you ever connecting it to anything. You've actually already encountered a gentle version of pressure changing what liquids do. If you've ever tried cooking at high altitude, climbers and hikers who cook meals at the top of tall mountains have to adjust their recipes, because water boils at a noticeably lower temperature up there. At the summit of Mount Everest, for instance, water boils at around 70 degrees Celsius rather than the sea level standard of 100, simply because the surrounding air pressure at that altitude is roughly a third of what it is at sea level. Instructions for cooking pasta or boiling eggs actually change depending on elevation for exactly this reason. A small, everyday piece of evidence that boiling has always been about pressure as much as heat, hiding in plain sight in cookbooks without most people ever connecting it to the deeper physics involved. Mountaineers on peaks like Everest have long joked about how difficult it is to properly cook rice or brew a decent cup of tea at extreme altitude, precisely because the water simply won't get hot enough to cook food the way it does at sea level, no matter how long you leave it boiling, since it's already converting to steam at a temperature too low to fully cook most foods. This is worth pausing on, because it genuinely defies the intuition most of us grew up with about boiling. We learn as kids that water boils at 100 degrees Celsius, and we treat that number like it's a fixed, universal law, true everywhere, all the time. It isn't. That specific boiling point only applies at Earth's normal sea level pressure. Boiling isn't really about reaching some magic temperature at all. It's about the point where a liquid's own vapor pressure, the tendency of some of its molecules to want to escape into gas form, finally overcomes the pressure of the atmosphere pushing down on it and holding it together as a liquid. Turn down the outside pressure enough and water will boil at room temperature or at body temperature, or even in an extreme enough vacuum while sitting in a glass of ice water, because the temperature was never really the deciding factor. The pressure was. It's a genuinely strange thing to realize once you actually sit with it. Boiling was never really a statement about heat at all. It was always a statement about the relationship between two competing pressures. One pushing out from inside the liquid, one pushing in from the surrounding atmosphere. And everything you thought you knew about a fixed, universal boiling point was really just describing what happens to that relationship under one specific, familiar set of conditions. Now hold that fact in your mind for a second, and let's bring it back to Mars, and to your own body, because this is where the real answer to tonight's question finally comes together. There's a specific, well-documented threshold in aerospace medicine called the Armstrong limit, named after Harry Armstrong, a flight surgeon who did pioneering research into exactly this kind of extreme, high-altitude physiology in the early 20th century, at a time when aviation was pushing pilots to altitudes higher than anyone had previously survived. And nobody yet fully understood what the human body's actual limits were. Armstrong's research, conducted using pressure chambers designed to simulate the thin air found at extreme altitudes, helped establish exactly where the human body's fluids stop behaving the way we expect them to at sea level. Work that became foundational to the entire field of aerospace medicine and remains directly relevant to human spaceflight safety to this day. The Armstrong limit sits at an atmospheric pressure of about 6.3 kilopascals, roughly equivalent to the pressure you'd experience at an altitude of around 19 kilometers above Earth's surface. well above where commercial aeroplanes fly in the thin upper reaches of the stratosphere. Below that specific pressure threshold, something happens to exposed body fluids that has nothing to do with temperature at all. Water and the water-based fluids that make up the vast majority of your body boils not because it's being heated, but because there simply isn't enough outside pressure holding the liquid together in its liquid form anymore. And here, finally, is the actual answer to tonight's question. Mars's atmospheric pressure at roughly 600 pascals sits nearly 10 times below that 6.3 kilopascal Armstrong limit threshold, comfortably, catastrophically below the point where your own body fluids can remain stable liquids when directly exposed to that environment. The thing that would kill you first on Mars isn't the cold, and it isn't a simple lack of breathable oxygen in the way most people picture suffocation. It's the mechanical failure of your own body's fluids. The moisture on your tongue, in your eyes, and deep in your throat would begin to boil, not because Mars is hot, it's freezing, but purely because of pressure. And it would start within seconds, long before the cold has a chance to matter, long before you've even run out of the oxygen already in your lungs. Take a second to actually notice how strange that answer is once it's finally sitting in front of you plainly. Not radiation, not a dramatic freeze, not some exotic Martian toxin, just pressure. A concept so basic and so invisible in your everyday life that it probably never once occurred to you as a candidate answer before tonight, and yet it turns out to be the single fastest, most certain way this particular planet would end a human life. So if your gut guess a few minutes ago was cold or suffocation, you were in good company, and you weren't exactly wrong, just early. Both of those things are real threats on Mars, and we're going to get to exactly where they rank in a moment. But neither of them is what actually gets you first. Let's walk through exactly what this looks like, moment by moment, because the specifics matter, and I want to be honest about exactly where the science is well established, and exactly where we're reasoning from related evidence rather than direct human testing, since nobody has ever actually done this and lived to describe it in full, for reasons that will become obvious as we go. It's worth pausing here to note where all of this actually comes from, because none of it is guesswork. Every number we've walked through so far, and every one still ahead of us, has been measured directly by spacecraft that have actually landed on or orbited Mars. Combined with decades of aerospace medicine research conducted here on Earth using pressure chambers, animal studies, and, in a small number of documented cases, real human accidents. This isn't a thought experiment built on speculation. It's a thought experiment built entirely on evidence that already exists, just rarely assembled together in one place the way we're doing tonight. The very first tissues affected would be the ones already exposed directly to the outside environment. Your eyes, the inside of your mouth, your tongue, the surface of your throat. Within seconds, based on decades of research into rapid decompression incidents involving aircraft and spacecraft, the moisture on these exposed surfaces would begin to vaporize rapidly, a process doctors and physiologists call ebullition, from the Latin word for boiling. This isn't a slow simmer, it's a rapid, visible transition. Saliva and tears essentially fizzing away into vapor, and it would almost certainly be intensely painful, along with likely causing your face and the exposed surfaces of your body to swell noticeably, based on what's been observed in both the animal studies and the rare human incidents on record. As gases dissolved in your blood and other bodily fluids begin coming out of solution and forming bubbles, a process closely related to what scuba divers experience with decompression sickness, sometimes called the bends, if they surface from deep water too quickly, except happening far more severely and far more quickly, because the pressure difference involved is so much more extreme. Try to actually picture the sequence rather than just the label embolism, because the label alone doesn't quite convey what's happening. It's not your whole body suddenly boiling like a pot of water. It's specifically the exposed, moisture-rich surfaces, the ones with no skin barrier between them and the outside atmosphere, that begin this process first and fastest, while the rest of your body, still protected by skin, follows a slightly different and slightly slower path toward the same basic outcome, as the pressure differential works on tissues just beneath the surface. Divers who've experienced even mild decompression sickness describe it as one of the more distinctly awful sensations the human body can produce. A deep, aching, wrong feeling as gas bubbles form in joints and tissues that were never built to accommodate them. The condition got its nickname, the bends, from the way affected divers in the 19th century. Often construction workers who'd been working in pressurized underwater or underground chambers called caissons would double over in pain, bending at the joints as bubbles formed in their tissues after surfacing too quickly. It's a condition serious enough that it fundamentally shaped how diving is taught and practiced today, with dive tables and computers specifically designed to calculate safe ascent rates that give the body time to release dissolved gases gradually rather than all at once. Scale that same basic mechanism up to the pressure differential involved in full exposure to Mars's near-vacuum atmosphere, happening throughout your entire body simultaneously rather than gradually in a few joints. And you start to get a sense of just how quickly and thoroughly this process would overwhelm a person, well before oxygen deprivation alone would have had time to become the dominant problem. I want to be genuinely careful here, because this is exactly the kind of moment where a video like this one could slide into exaggeration for shock value. And I'd rather give you the honest, evidence-based picture instead. We actually do have real data on human exposure to near-vacuum conditions, tragically, from a small number of documented accidents involving high-altitude aircraft and spacecraft depressurization, along with extensive animal studies conducted specifically to understand this exact scenario for the sake of astronaut safety. Based on that evidence, a human exposed to a near-vacuum environment, one where the pressure is at or below the Armstrong limit, would very likely remain conscious for somewhere in the range of 10 to 15 seconds. This isn't because the body somehow holds together for that long. It's because that's roughly how long the oxygen already circulating in your bloodstream, delivered by your last full breath before exposure, continues to keep your brain minimally functional before the combination of oxygen deprivation and the physical effects of embolism overwhelms you and you lose consciousness. Based on how quickly this kind of decompression unfolds, and based on how nerve signals travel at finite, measurable speeds through the human body, roughly on the order of 100 meters per second for the fastest nerve fibers we have, it's reasonable to infer that any pain signal generated by the initial embolism would have at absolute most a handful of seconds to reach your brain and be consciously processed before unconsciousness set in, which suggests, though it can't be stated with total certainty, that the experience, however unpleasant, would be brief. It's worth being clear that this specific window, 10 to 15 seconds, comes primarily from data involving true vacuum exposure rather than Mars's specific near-vacuum atmosphere, so applying it directly to Mars involves a reasonable, evidence-based extrapolation rather than a number measured under the exact conditions we're describing tonight. A distinction worth keeping in mind as we continue. Some researchers who've specifically modeled Mars's atmosphere as opposed to true vacuum note that the small amount of residual gas pressure present, even at 600 pascals, might theoretically slow certain aspects of the embolism process by a small amount compared to a true, complete vacuum, though the overall timeline and outcome would remain broadly similar, since 600 pascals is still so far below the Armstrong limit that the qualitative behavior doesn't meaningfully change. This is exactly the kind of place where good science communication has to hold two things at once: confidence in the underlying physics, which is extremely well established, alongside honesty about the fact that the precise number of seconds involved is an informed estimate rather than a directly measured fact for this specific scenario. We actually have one real documented human account that lines up almost perfectly with everything we've just described. In December of 1966, a NASA test subject named Jim LeBlanc, a spacesuit technician working in a vacuum chamber at what's now called the Johnson Space Center in Houston, was testing an early prototype moonsuit when his pressurization hose accidentally disconnected, dropping the pressure inside his suit from about 3.8 pounds per square inch down to just 0.1 pounds per square inch, a near total vacuum, in under 10 seconds. Exposing him to conditions equivalent to an altitude of roughly 36 kilometers, well above the Armstrong limit. According to LeBlanc's own later account and the medical records from the incident, he remained conscious for approximately 14 seconds before passing out, and he specifically recalled feeling the saliva on his tongue begin to bubble in the instant just before he blacked out. A detail that lines up almost exactly with what the underlying physics predicts. A colleague rushed in and manually repressurized the chamber, and full atmospheric pressure was restored within about 87 seconds, nearly a minute and a half after the accident began. LeBlanc had already regained consciousness by that point and, remarkably, suffered no lasting injury beyond a temporary earache, providing one of the very few genuine, if unintentional, first-hand human accounts of exactly the process we've been walking through tonight. An account that has since become something of a foundational case study cited in aerospace medicine training precisely because it confirms from direct human experience so much of what theory alone had only predicted. It's a genuinely remarkable thing, when you sit with it, that one of our best pieces of direct evidence for exactly this scenario comes not from a deliberate experiment, but from a single accidental moment in a Houston test facility nearly 60 years ago, preserved because one technician happened to survive it and happened to remember, with striking clarity, exactly what the last conscious seconds felt like. Now, I want to be honest about something else here, because it's an important distinction that a lot of casual explanations of this topic get slightly wrong. and getting it right actually makes the whole picture more interesting rather than less. Popular culture, especially older science fiction, sometimes portrays exposure to a vacuum-like environment as causing a person's body to violently explode. Blood vessels bursting, the whole body swelling up catastrophically and rupturing within an instant. Based on the actual medical evidence we have, including LeBlanc's own case, that dramatic version isn't accurate. Not for space's true vacuum, and not for Mars's near-vacuum atmosphere either. Human skin, it turns out, is considerably tougher and more elastic than most people assume, easily strong enough to contain the pressure differential involved without simply bursting apart. In much the same way a sealed bag of chips doesn't violently explode when you take it up a mountain, even though it does noticeably puff up as the outside pressure drops relative to the pressure trapped inside. What actually happens is closer to significant swelling, especially in soft, unprotected tissues, along with the embolism we've already discussed affecting exposed moist surfaces, rather than anything resembling an explosion. The real danger isn't your body failing structurally. It's the combination of oxygen deprivation, the physical shock and pain of embolism affecting your eyes, mouth and throat, and a cold finally beginning to compound these effects as the seconds pass, all working together. None of them needing to be as cinematically dramatic as popular imagination often assumes, in order to be genuinely and swiftly lethal. I think this deserves a moment of real reflection, because it reframes something people don't usually think about regarding their own bodies. We tend to think of air purely in terms of its chemistry, oxygen going in, carbon dioxide coming out, the stuff your lungs are built to process. But your body depends on the atmosphere around it for something entirely separate from that chemical exchange: sheer mechanical pressure, holding your fluids together in the state they need to be in for your cells and tissues to function at all. It's a dependency so constant and so completely reliable throughout your entire life that you've never had a single reason to notice it. The same way a fish never has to consciously appreciate water pressure until the day it's suddenly, catastrophically absent. Think about everything happening in your body right now, at this exact moment, that depends on this invisible mechanical support. The blood moving through your veins depends on it. The fluid cushioning your joints depends on it. Even the simple, unconscious act of blinking depends on your tear film remaining a stable liquid rather than instantly vaporizing off the surface of your eye. None of this ever crosses your mind, because it's never had a reason to. Deep sea fish offer a strange inverted mirror of this same idea. Certain species that live at crushing ocean depths have evolved entire bodies calibrated to the immense pressure of the deep sea, and when accidentally brought up to the surface too quickly by a fishing net or a submersible's mistake, their bodies suffer catastrophic damage from the sudden pressure drop, organs shifting, swim bladders rupturing, sometimes eyes bulging outward. A vivid demonstration of just how completely a living body can become calibrated to one specific pressure environment, and just how badly that calibration can fail when the surrounding pressure changes too quickly for the body to adjust. You are, in your own way, exactly that kind of pressure-calibrated creature, just calibrated to a gentler, more familiar environment than the deep ocean. One you've simply never had to think about because Earth's surface has never once in your entire life asked you to. Let's talk about exactly why Mars ended up with this thin, oxygen-poor atmosphere in the first place. Because it's not a random quirk of the planet. It comes down to two connected reasons, and understanding them helps explain why this specific danger. Of all the dangers Mars presents is the fastest acting one. The first reason is Mars's mass. Mars is considerably smaller than Earth, with only about 38% of Earth's surface gravity, which means Mars's gravitational pull is simply weaker at holding on to a thick blanket of gas around itself. Gravity in this context works essentially like a leash, constantly pulling gas molecules back down toward the planet's surface, keeping them from drifting off into space. A smaller, lower-gravity planet like Mars has a weaker leash, meaning gas molecules, especially lighter ones moving at higher speeds, find it easier to escape entirely. To put Mars's size in perspective, its total diameter is only about half of Earth's, and its total mass comes out to roughly 1/10 of Earth's, meaning you could fit several Mars-sized planets inside a single Earth with room to spare. That reduction in mass isn't a small incidental difference. It fundamentally changes how strongly the planet can hold on to anything, atmosphere included, over the vast timescales involved in planetary history. The second, and arguably more important, reason is Mars's missing global magnetic field. Earth's molten iron core generates a magnetic field that extends out into space, deflecting most of the charged particles streaming outward from the Sun, the solar wind, before they can strip away our atmosphere. You can actually see this magnetic shield in action here on Earth in the form of the aurora, the northern and southern lights, which occur when solar wind particles get funneled by our planet's magnetic field down toward the poles, where they collide with atmospheric gases and produce that famous glow. It's a beautiful, visible reminder that our planet is actively fighting off a constant bombardment of solar particles every single day, using a shield most of us never think about. Mars has its own faint, localized magnetic fields, frozen into patches of its ancient crust, remnants of the global field it once had, but nothing resembling a coherent, planet-wide shield capable of doing what Earth's magnetic field does. Spacecraft studying Mars have actually detected faint, localized auroras there too, in the ultraviolet range invisible to human eyes, produced by solar particles interacting with these leftover crustal magnetic patches, a strange, ghostly echo of the much stronger shield Mars used to have. Mars, based on measurements taken by orbiting spacecraft studying exactly this question, lost its own global magnetic field somewhere around 4 billion years ago, likely because its smaller size allowed its core to cool and its internal dynamo, the process that generates a planetary magnetic field, to shut down far earlier in its history than Earth's did. Without that magnetic shield, the solar wind has spent billions of years slowly, steadily stripping away Mars's original atmosphere, particle by particle, carrying it off into space, leaving behind the thin, wispy remnant we find there today. A remnant so thin it sits below the exact threshold your own body needs to keep its fluids from boiling away the moment they're exposed. There's something worth sitting with in that fact, because it means the very danger that would kill you fastest on Mars isn't really about Mars itself, in isolation. It's about a planetary history spanning billions of years, a molten core cooling faster than Earth's did, a magnetic field switching off, a thin atmosphere slowly bleeding away into space, particle by particle, under the relentless pressure of the solar wind, all of it converging, eventually on a single number, 600 pascals. It's a strange kind of causality to hold in your head all at once. The reason your saliva would boil within 10 seconds of stepping onto Mars traces back in an unbroken chain to decisions made by physics itself billions of years ago, when Mars's core, smaller and faster cooling than Earth's, lost the internal heat needed to keep generating a planet-wide magnetic field. Every single second since then, for 4 billion years, the solar wind has been quietly, patiently doing its slow work, and the bill for that 4 billion year process comes due for a human visitor in about the time it takes to read this sentence out loud. There's a related detail worth clarifying here too, because it's easy to blur together with the pressure problem even though it's technically a separate issue. Even setting aside pressure entirely, even in some hypothetical scenario where Mars's atmosphere sat at a comfortable Earth-like pressure, you still couldn't breathe it, because of what it's actually made of. Mars's atmosphere is roughly 95% carbon dioxide, with small amounts of nitrogen and argon rounding out most of the rest, and only a tiny trace of oxygen, well under 1%. Compare that to Earth's atmosphere, which is roughly 78% nitrogen and 21% oxygen, with carbon dioxide making up a mere fraction of 1%. And you get a sense of just how completely inverted Mars's atmospheric chemistry is compared to what our lungs actually evolved to process. Breathing pure carbon dioxide or an atmosphere with only trace oxygen would cause a rapid buildup of carbon dioxide in your own bloodstream, leading to a specific, distinct kind of distress separate from simple suffocation, one your body actually has dedicated sensors for. Your brain doesn't primarily monitor how much oxygen you're getting to decide when you need to breathe. It monitors carbon dioxide levels in your blood, which is why breathing an atmosphere heavy in carbon dioxide produces such an intense, panicked urge to breathe faster and harder. Your body desperately trying to flush out a gas it's built to treat as an emergency signal, even though in this specific scenario, breathing harder would only pull in more of the very gas, causing the problem in the first place. It's a strange, almost cruel design quirk of human physiology in this exact context. The very warning system meant to protect you, the urgent, overwhelming need to breathe when carbon dioxide builds up, would actively work against you here, driving you to breathe in more of the exact gas mixture, making things worse. It's a reminder that our bodies were shaped entirely by conditions on one specific planet, tuned exquisitely to Earth's exact atmospheric chemistry over hundreds of millions of years of evolution, with absolutely no allowance built in for an environment where the sensible, protective response, breathe harder, becomes the wrong one entirely. This composition problem is real, and it's exactly why any realistic human presence on Mars requires a fully sealed, self-contained breathing system, not just something that filters or pressurizes the outside air. Every habitat and suit design ever seriously proposed for Mars carries its own oxygen supply, generated either from stored reserves or extracted directly from Martian resources like subsurface ice and atmospheric carbon dioxide, precisely because you can't simply pressurize the outside atmosphere and breathe it safely, the way you might imagine doing with a sealed dome pumped full of compressed Martian air. The composition, not just the pressure, would still need to be fundamentally re-engineered before it could sustain a human being. But in the specific full exposure scenario we've been walking through tonight, this chemistry issue never really gets the chance to become the dominant problem either. For the exact same reason cold doesn't, the raw pressure problem resolves things first, within that same 10 to 15 second window. Let's actually give the cold its proper due here though, because it's a genuinely brutal feature of Mars, even if it's not the fastest acting one. Average surface temperatures on Mars hover around minus 63 degrees Celsius, roughly minus 81 degrees Fahrenheit, colder than almost anywhere on Earth experiences as a yearly average, comparable to some of the coldest recorded temperatures in Antarctica. But Mars's temperature swings are what really set it apart from anywhere on Earth. Because the atmosphere is so thin and holds on to so little heat, temperatures on Mars can swing by 50 to 80 degrees Celsius between daytime highs and nighttime lows at the exact same location. An enormous daily temperature roller coaster that dwarfs anything experienced on Earth, where oceans and a thicker atmosphere work together to smooth out day to night temperature swings considerably. A relatively mild Martian summer afternoon near the equator might reach a downright pleasant 20 degrees Celsius, 68 degrees Fahrenheit. Warm enough that you could stand there in a t-shirt and, temperature alone, feel reasonably comfortable if it weren't for that 600-pascal pressure problem we just spent this entire conversation on. Come nightfall, that same spot can plunge to minus 70 degrees Celsius or colder within a matter of hours. An almost unbelievable swing that happens, quite literally. Every single day on Mars, driven by an atmosphere too thin to hold on to the sun's warmth once it sets. Picture standing on the Martian surface at local noon, in that pleasant 20-degree warmth, and then watching the sun begin to set. Within a few hours, as the ground rapidly radiates its heat away into a thin atmosphere too sparse to trap it, the temperature would fall as steeply as if someone were opening a giant freezer door directly in front of you, dropping perhaps a full degree Celsius every few minutes. An experience genuinely without a good comparison anywhere on Earth's surface, where the ocean's vast heat capacity smooths out even the most extreme desert day to night swings. Cold is a genuine, serious threat on Mars, and in a scenario where someone's suit or habitat failed in a way that primarily compromised insulation and heating rather than causing total pressure loss, cold would absolutely become the dominant, most urgent danger, potentially over a timescale of minutes rather than seconds, which is a meaningfully longer window to notice a problem and respond to it. It's a genuinely counterintuitive detail worth sitting with though. Mars's thin atmosphere is actually a fairly poor conductor of heat, precisely because it's so thin, meaning that despite the brutally low average temperatures, the actual rate at which your body would lose heat to that thin surrounding air, in the specific scenario of full exposure alongside the pressure catastrophe, is considerably slower than you'd experience standing outside on an equally cold day on Earth, where thicker, more heat-conductive air would pull warmth away from your skin far more efficiently. But in the specific scenario of full, unprotected exposure to Mars's outside atmosphere, the one most people instinctively picture when they imagine this question, cold simply doesn't get the chance to be the fastest killer. because the pressure problem resolves the situation, one way or another, long before hypothermia would have time to develop. So if you're keeping score at home, pressure first, cold second, breathable air chemistry third, all of it happening within a window of seconds to at most a few minutes, depending on exactly what fails and how. It's a genuinely useful mental checkpoint to hold on to, because it already overturns the instinctive ranking most people, understandably, would have written down before tonight: cold first, suffocation second, pressure not even on the list. But that's actually not where Mars's dangers end, and it's not even where the most surprising twists in this story are, because the scenario we just walked through, full, sudden, complete exposure with no protection whatsoever, is actually one of the less likely ways an unprotected exposure to Mars would realistically happen, at least in the context of an actual mission gone wrong, rather than a deliberately reckless thought experiment. Real accidents, the kind space agencies plan extensively to avoid and to survive if they somehow occur anyway, are far more likely to involve a partial suit breach, a small puncture, a failed seal, a torn glove, rather than a person simply stepping outside completely naked into the Martian atmosphere. Consider how a real Mars mission would actually be structured, with astronauts spending the overwhelming majority of their time either inside a pressurized habitat or inside a pressurized suit specifically engineered to maintain something close to Earth normal pressure around their body, even while surrounded by Mars's thin outside atmosphere. Modern spacesuit design, refined over decades of spacewalks and lunar missions, is built around exactly this challenge, maintaining a stable internal pressure bubble around a human body in an environment that would otherwise be lethal within seconds, as we've just spent this entire conversation establishing. A suit failure, then, isn't really exposure to Mars. It's a much more specific, much more survivable in principle scenario. A slow or partial leak in that carefully maintained pressure bubble, giving a person and their crewmates at least some window of time to notice the problem and respond, rather than the instantaneous, total exposure we've been describing as the worst-case scenario. And the specific sequence of what kills you first changes in genuinely interesting ways depending on exactly which part of that protective barrier fails, how large the breach is, and how quickly it's noticed and addressed. A pinhole leak in a glove behaves completely differently than a torn seam across the torso, which behaves differently again from a catastrophic, sudden loss of the entire suit's pressure integrity. Some of these failure modes give you minutes to react, others give you seconds. Understanding which is which and why turns out to be one of the more practically important pieces of knowledge underlying real spacesuit engineering, not just an interesting thought experiment for a video like this one. And once you're safely back inside a pressurized habitat, breathing filtered, oxygen-rich air again, an entirely different, much slower category of threats starts working on you instead. Ones that don't announce themselves with an immediate emergency at all, the toxic chemistry of the Martian soil itself, radiation with a reputation far scarier than its actual danger profile deserves, and the slow, quiet toll of gravity itself, at just over a third of Earth's, reshaping your body in ways you wouldn't even notice happening until months later. Each of these threats deserves the same careful, honest treatment we just gave to pressure and embolism. separating what the evidence firmly establishes from what remains a reasonable, well-grounded inference, and ranking them not by how dramatic or frightening they sound, but by how quickly and how certainly they'd actually end a human life on Mars. Some of these slower threats, it turns out, are ranked in an order that would probably surprise you almost as much as the pressure answer already has, and building out that complete, honest hierarchy, fastest to slowest, real danger versus reputation, is exactly where we're headed next. Keep your original guess in mind: cold or lack of air. Because by the time we finish building out this complete ranking, you're going to see exactly how far off, or how close, that first instinct actually was, and which of Mars's dangers deserves your attention far more than its reputation currently suggests it should. Let's start with the one that has the scariest reputation of all: radiation. Mars lacks not just a global magnetic field, as we've already discussed, but also the thick, protective blanket of atmosphere that shields Earth's surface from a constant rain of high-energy particles arriving from deep space, called galactic cosmic rays, along with occasional bursts of particles thrown out by the Sun itself during solar storms. These galactic cosmic rays are themselves a genuinely strange phenomenon worth understanding a little, since they're not something the Sun produces at all. They're thought to originate from far more violent events scattered across the galaxy, the explosive deaths of massive stars in supernovae, and the extreme environments surrounding black holes and neutron stars, accelerating charged particles to speeds close to the speed of light before they go wandering through the galaxy for millions of years, eventually crossing paths with whatever planet happens to be in their way. It's a strange thought to sit with for a moment, some of the particles striking Mars's surface right now, and a smaller number reaching Earth's surface despite our planet's considerably better shielding, may have been accelerated by an explosion that happened millions of years before humans ever existed, around a star system we'll likely never identify, having traveled an almost incomprehensible distance across the galaxy just to arrive, at this exact moment, at whatever happens to be sitting on the ground beneath them. On Earth, our atmosphere and magnetic field together absorb the overwhelming majority of this radiation before it ever reaches ground level. Even astronauts flying at high altitude on commercial airliners, thousands of feet closer to space than the rest of us, absorb noticeably more radiation per hour than people standing at sea level, simply from spending time above a meaningful fraction of Earth's protective atmosphere. A detail that's part of why long-haul pilots and flight crews are actually tracked for cumulative radiation exposure as an occupational health consideration, with some studies suggesting frequent flyer crew members accumulate a meaningfully higher annual radiation dose than the average ground-based person, simply from the cumulative effect of many hours spent at cruising altitude over the course of a career. It's a genuinely useful, close-to-home comparison for understanding how thin, in relative terms, even Earth's much thicker atmosphere becomes once you climb high enough, and it hints at just how much more exposed Mars's surface, with an atmosphere roughly 100 times thinner still, would actually be. On Mars, with essentially neither of those protections intact, a much larger share of this same radiation reaches the surface directly, unfiltered by any comparable planetary shield. Here's where the popular imagination and the actual measured reality diverge sharply, though. Science fiction has trained most of us to think of radiation exposure as something fast and dramatic, a burst of energy that might knock you unconscious or visibly burn you within moments. The kind of danger you'd need to sprint away from. The real measurements tell an entirely different story. NASA's Curiosity rover carries an instrument called the Radiation Assessment Detector, specifically designed to measure exactly this kind of exposure. And it has been recording data on the Martian surface continuously since the rover landed in 2012. Based on years of that actual measured data, the average radiation dose rate on Mars's surface comes out to somewhere around 0.64 to 0.67 millisieverts per day. To put that in perspective, that's a meaningful amount of radiation, roughly comparable to what an average person on Earth might absorb from all natural background sources combined over the course of an entire week. But it's absolutely nowhere close to being an immediate, dramatic threat. You could stand on the surface of Mars unshielded for an entire day, and the radiation alone wouldn't harm you in any way you'd notice at the time. The danger from Martian radiation is cumulative, not immediate, and that distinction changes everything about how it should be ranked among Mars's threats. Based on that measured daily dose rate, a mission involving roughly 500 days on the Martian surface, a reasonably realistic duration for an actual crewed mission given how planetary orbits align, would expose an astronaut to somewhere in the neighborhood of a third of a sievert total, once you factor in the additional radiation absorbed during the journey there and back through open space, where there's no planetary shielding at all. For context, medical and safety agencies generally associate a cumulative dose of around 1 sievert with roughly a 5% increase in lifetime risk of fatal cancer, a serious, real consideration for long-duration astronauts, but a risk that unfolds over years and decades of increased cancer probability, not a risk that kills you on the spot the way a suit breach would. It's the difference between stepping into traffic, an immediate, obvious danger, and smoking cigarettes for a decade. A genuine, serious health risk that nonetheless takes its toll slowly, quietly, in the background, without any single dramatic moment where the danger announces itself. Nobody smoking their first cigarette collapses on the spot, and nobody would collapse from a single day's dose of Martian radiation either. The harm in both cases comes from sustained, repeated exposure accumulating quietly over a timescale measured in years, not from any single instance being independently dangerous enough to notice in the moment. It's a genuinely useful comparison for recalibrating how we intuitively think about radiation risk, since most people's mental model of radiation danger comes from either nuclear disaster movies involving sudden, massive, acutely lethal doses, or from vague, poorly specified anxiety, neither of which maps well onto the actual, well-characterized, slow accumulating risk profile Mars's surface radiation genuinely presents. It's worth noting, too, that this comparison isn't meant to minimize the real risk radiation poses to long-duration Mars missions. Mission planners take it seriously enough that habitat designs specifically incorporate radiation shielding, often using the Martian regolith itself piled over living quarters as a cheap, effective barrier against incoming cosmic rays. And mission durations and crew rotation schedules get calculated with cumulative dose limits explicitly in mind. The point isn't that radiation doesn't matter. It's that it matters on a completely different timescale and through a completely different mechanism than the fast, dramatic threats most people instinctively picture when Mars radiation comes up in conversation. I think it's worth being explicit here about exactly why this matters for correctly ranking Mars's dangers. Because it's easy to let a word like radiation trigger an automatic assumption of extreme immediate danger, when the actual measured reality is considerably more nuanced. Part of this comes down to how radiation has been portrayed in popular culture for the better part of a century. Ever since the earliest nuclear weapons tests and reactor accidents gave the public a set of extremely dramatic, extremely visible images to associate with the word sudden illness, visible burns, dramatic and rapid death. Those images are accurate for the specific, acute, massive doses involved in a nuclear weapon's immediate blast radius or a severe reactor meltdown. But they've also trained most of us to expect that same drama from any mention of radiation exposure at all, regardless of the actual dose involved. Which is exactly the kind of mismatch between reputation and reality that a careful evidence-based ranking has to correct for. Based on the numbers we just walked through, if you're building an honest hierarchy of what would actually kill a person on Mars ranked by speed and certainty, radiation lands nowhere near the top. It's a real serious concern for long-duration missions, one that mission planners take extremely seriously when designing habitat shielding and calculating safe mission lengths. But as a fast-acting killer, in the way this video's title is really asking about, it simply isn't one. Someone could survive months on Mars's surface with radiation as statistically one of the least urgent problems they're dealing with day to day, even while it quietly accumulates a genuine long-term health cost in the background, the kind of cost that might not become medically apparent until years after the astronaut has safely returned home. Now let's talk about the ground itself, because Mars has a chemical secret buried in its soil that most casual explanations of Mars survival skip over entirely, and it's one of the more genuinely nasty surprises in this whole conversation. In 2008, NASA's Phoenix lander touched down in Mars's northern plains and, among its other scientific instruments, carried equipment specifically designed to analyze the chemical composition of the Martian soil. What it found, confirmed by subsequent missions including the Curiosity rover exploring a different region entirely, was the widespread presence of perchlorate salts, chemical compounds containing chlorine and oxygen distributed across the Martian surface at concentrations somewhere between roughly 0.4% and a full 1% by weight, depending on the specific location sampled. The discovery genuinely caught the Phoenix science team off guard. By some accounts from scientists involved in the mission, perchlorate wasn't even a word most of the team recognized offhand when the readings first came back, an obscure enough chemical term that researchers had to look it up to confirm exactly what they were looking at. That's a small human detail worth sitting with. One of the most important chemical discoveries about the Martian surface, a compound that fundamentally shapes how future human missions will need to be designed, was initially met with a room full of experienced planetary scientists needing to consult a reference book. A reminder that even the most well-prepared missions to other worlds regularly turn up genuine surprises nobody had specifically anticipated, no matter how carefully the mission was planned or how many decades of prior Mars research came before it. That might sound like a small amount, but it's actually an extraordinarily high concentration compared to anything found naturally occurring on Earth's surface, where perchlorates typically only accumulate in trace amounts in a handful of the driest deserts on the planet. Like Chile's Atacama Desert, one of the closest things Earth has to a genuine Mars analog environment. Researchers have long studied the Atacama specifically because its extreme dryness, low biological activity, and unusual soil chemistry make it one of the best available stand-ins for Martian conditions. And the discovery of naturally occurring perchlorate there, in trace amounts, helped researchers recognize and properly interpret the far higher concentrations Phoenix eventually found on Mars itself. The Atacama's own perchlorate deposits, interestingly, have been commercially significant on Earth for over a century, mined as a natural source of nitrate fertilizer and, more relevantly, once processed industrially to extract perchlorate itself for use in rocket propellant and fireworks. A strange small connection between an ordinary Earth desert and the very rockets that would eventually carry humans toward the planet where that same chemical waits in vastly greater abundance. Perchlorates are toxic to humans specifically because they interfere with your thyroid gland's ability to absorb iodide, a substance your thyroid needs in order to produce the hormones that regulate your metabolism, growth, and a wide range of other bodily functions. Interestingly, and this is a detail that adds a genuinely strange layer to the story, potassium perchlorate was actually used as a legitimate medical treatment for hyperthyroidism, an overactive thyroid, back in the 1950s and 1960s. Precisely because of this thyroid blocking effect, prescribed deliberately to patients whose thyroid glands were producing too much hormone. Doctors at the time recognized that the same mechanism making perchlorate hazardous in an uncontrolled exposure could be turned into a useful, precisely dosed treatment for a specific medical condition, competitively blocking iodide uptake just enough to bring an overactive thyroid back into a healthier range. That medical use was eventually discontinued after a small number of patients developed serious blood disorders as a side effect, including a rare but dangerous condition where the bone marrow stops producing enough white blood cells, alongside cases of aplastic anemia, a serious failure of the bone marrow to produce enough new blood cells generally, prompting doctors to switch to other, better tolerated antithyroid medications that have remained in use ever since. The underlying point remains, though, perchlorate's toxicity isn't some exotic alien effect unique to Mars. It's a well-characterized, well-studied chemical hazard that human medicine has actually dealt with directly, right here on Earth, decades before anyone thought to look for it on another planet. For an astronaut on Mars, the danger comes primarily through inhalation and ingestion, not simple skin contact, since perchlorate doesn't absorb particularly well through intact skin. Mars is extremely fine, pervasive dust though, which tends to work its way into everything, habitat seals, equipment joints, and inevitably, despite every precaution, breathing air and food and water supplies over the course of an extended mission creates exactly the kind of chronic, low-level exposure pathway that would matter most. Martian dust is notoriously fine, with individual particles often smaller than the width of a human hair, fine enough to be stirred up by the gentlest breeze and to work its way past seals and filters that would easily stop coarser terrestrial dust. A genuine engineering headache that every rover and lander mission has had to contend with. and one that a human habitat would need to solve considerably more thoroughly, given the added stakes of a crew actually breathing that air day after day for months at a time. Based on what's known about perchlorate toxicity in humans from decades of medical and industrial exposure studies here on Earth, sustained exposure at the concentrations found in Martian soil would likely produce a slow, cumulative thyroid disruption, similar in its underlying mechanism to the deliberate medical use we just discussed, but chronic and unintentional rather than a carefully managed short-term treatment. Left unaddressed over months, this could contribute to fatigue, metabolic disruption, and in vulnerable individuals or with sufficiently high accumulated exposure, more serious complications. Though it's worth being clear that we don't have direct, long-term human exposure data at Martian dust concentrations specifically, since nobody has actually lived on Mars long enough to generate that data. What we have instead is a well-grounded extrapolation from known perchlorate toxicity thresholds studied extensively here on Earth, applied to the specific concentrations Mars missions have actually measured. A reasonable and scientifically defensible inference, but an inference nonetheless, rather than a directly confirmed fact about human health on Mars specifically. This puts perchlorate poisoning in a genuinely interesting spot on our hazard ranking, closer to radiation than to the sudden catastrophic pressure loss we covered earlier. It's a real serious threat that any actual Mars mission would need extensive engineering safeguards to manage. Dust filtration, careful decontamination procedures, sealed habitat entry protocols, but it's fundamentally a slow-acting, cumulative danger rather than something that would kill an astronaut within minutes or hours of exposure. Acute, massive perchlorate poisoning, the kind involving direct ingestion of a large quantity, is a different and far more dangerous story, capable of causing severe, rapid harm through disruption of your blood's oxygen carrying capacity and damage to your kidneys, with research on acute toxicity suggesting that a dose in the range of several grams could be sufficient to cause serious, potentially fatal harm to an adult through this more direct mechanism. But that scenario would require directly consuming Martian soil or heavily perchlorate-contaminated water in significant quantity, not simply existing on the Martian surface, which is a meaningfully different and less likely failure mode than the atmospheric pressure catastrophe we opened tonight's story with. Any realistic Mars mission would process water extracted from Martian ice specifically to remove perchlorate before it ever reached a crew member's drinking supply. Precisely because mission planners are well aware of exactly this risk, making the acute poisoning scenario one that's specifically designed around and mitigated against, rather than one that would realistically catch a well-prepared crew by surprise, provided the water processing systems themselves continued functioning correctly throughout the mission, which is itself the kind of engineering reliability question every Mars mission plan has to take just as seriously as any of the more dramatic hazards we've discussed tonight. There's one more Martian hazard tied to that same fine, pervasive dust worth mentioning honestly, even though it deserves less alarm than perchlorate specifically. Mars experiences genuinely massive dust storms, sometimes growing large enough to engulf the entire planet, as happened memorably in 2018. an event significant enough that it ultimately ended the mission of NASA's long-running Opportunity rover, which relied on solar panels that became too coated in dust and too starved of sunlight to keep the rover's batteries charged through the storm's duration. Opportunity had already far outlived its original 90-day planned mission by that point, having operated successfully on the Martian surface for nearly 15 years, traveling a total distance across the Martian surface greater than any other off-world vehicle in history, and its final transmission back to Earth, received before the rover's batteries finally died in the darkness of that storm, has become something of a poignant footnote in the history of Mars exploration. Engineers and scientists who'd worked with the little rover for over a decade genuinely mourning its loss the way you might mourn a colleague, even though it was, in the end, just a very durable, very well-engineered machine. News coverage at the time captured something genuinely touching about that reaction. Seasoned engineers, people who work with hard data and mission timelines for a living, visibly emotional at a press conference discussing the end of a robot's operational life. A small, human reminder that even our machines can earn something close to genuine affection when they quietly, faithfully outperform every expectation for as long as Opportunity did. For a human crew inside a properly engineered habitat, a planet-wide dust storm represents a serious operational challenge. Reduced solar power, reduced visibility, potential strain on life support systems working harder to filter dust-laden air. But based on measurements taken during these storms by rovers already stationed on the surface, wind speeds during even the most severe Martian dust storms remain relatively modest by Earth standards, generally not exceeding somewhere around 30 meters per second, a stiff, blustery wind rather than anything resembling the violent, debris-hurling hurricane force winds Hollywood depictions of Martian dust storms tend to portray. This makes sense once you remember Mars's atmosphere is so thin to begin with. Even fast-moving Martian air simply doesn't carry the same physical force as equivalently fast winds would in Earth's much denser atmosphere, since the force wind exerts on an object depends heavily on the density of the air doing the pushing, not just its speed. A 30-meter-per-second wind on Mars would rustle a flag and kick up visible dust, but it wouldn't come close to knocking over a properly secured piece of equipment, let alone a person, the way an equivalent wind speed would in Earth's much thicker atmosphere. The real danger during a Martian dust storm isn't being physically battered by the wind. It's the cascading operational and chemical effects, reduced power, reduced visibility, and the fine perchlorate-laden dust getting stirred up and spread more widely than usual, working its way into equipment seals, air filtration systems, and habitat entryways with a persistence that mission engineers have to design around from the very beginning, rather than treating as an occasional inconvenience. Let's move now to the last major item on our list, one that's genuinely different in character from everything else we've discussed tonight, because it's not really a hazard in the traditional sense at all. It's simply a persistent, ongoing condition, one that would begin working on an astronaut's body from the very first moment they set foot on the Martian surface and never really stop for as long as they remained there: gravity, or more specifically, the lack of enough of it. Mars's surface gravity comes out to about 38% of Earth's, meaning an object, or a person, weighs a little over a third of what they would weigh back home. This might sound almost pleasant at first, And in some ways, for short-term comfort, it genuinely would be. Lighter movement, easier lifting. A kind of buoyant, springy feeling to walking and jumping that Apollo astronauts famously experienced in an even more extreme form on the Moon's still weaker gravity. Roughly 1/6 of Earth's. Footage of those astronauts bounding across the lunar surface in long, loping strides, occasionally losing their balance and tumbling in slow motion, captures something genuinely delightful about reduced gravity. And Mars, at more than twice the Moon's gravitational pull, would offer a somewhat more controlled, though still noticeably lighter, version of that same experience. But the human body, over hundreds of millions of years of evolution, calibrated every one of its major systems: bone density, muscle mass, cardiovascular function, fluid balance, to the specific constant demand of Earth's full gravity. And removing even a significant fraction of that demand without actively correcting for it has real, measurable, and in some respects serious consequences over time. It's worth remembering that gravity isn't just something your body passively experiences, it's something your body actively works against, every single moment, using muscle tension and bone strength that only stay robust because they're constantly being challenged by exactly this demand. Remove or reduce that demand, and your body, in its own quiet, efficient way, starts reallocating resources away from systems it no longer perceives as necessary. The same basic biological logic that causes an unused muscle to weaken or an unworn path through a garden to become overgrown. We actually have a substantial amount of real human data on how bodies respond when gravity's normal demand is removed, thanks to decades of astronauts spending extended periods aboard orbiting space stations in near total weightlessness. Based on that research, astronauts in microgravity typically lose bone density at a rate of roughly 1 to 1.5% per month in weight-bearing bones like the hip and spine. A rate of loss considerably faster than even the bone loss experienced by elderly patients with severe osteoporosis here on Earth, where bone density typically declines by perhaps 1 to 2% per year, rather than per month. Over a 6-month stay aboard an orbiting station, an astronaut without any countermeasures could plausibly lose a proportion of hip bone density that would otherwise take a decade or more to lose here on Earth through ordinary aging alone. Muscle mass, particularly in the legs and back, the muscles most heavily used simply fighting gravity during ordinary daily activity, atrophies significantly as well without a dedicated, rigorous exercise regimen, which is exactly why astronauts aboard orbiting stations spend a substantial portion of every single day, often upwards of 2 hours, on specialized resistance and cardiovascular equipment, treadmills with harnesses to simulate weight-bearing impact, and resistance machines using vacuum cylinders instead of traditional weights, since ordinary weights become effectively weightless themselves in orbit. All of this equipment is specifically engineered to force their bodies to keep doing the physical work that Earth's gravity would otherwise demand automatically, for free, every waking moment, a genuinely strange inversion, where astronauts have to work harder, not easier, to maintain the basic physical condition that gravity used to provide automatically back home. Here's where I need to be genuinely careful about the difference between established fact and reasonable extrapolation, because this is exactly the kind of place where a video like this one could overstate its certainty. all of that bone and muscle loss data comes from astronauts experiencing essentially zero gravity in continuous orbital freefall, not the partial 38% gravity Mars actually offers. Based on what we currently understand about how these physiological systems respond to mechanical loading, it's reasonable to assume that Mars's partial gravity would slow these effects considerably compared to full weightlessness, since your bones and muscles would still be doing some real work fighting gravity with every step. But we don't yet have direct, long-duration human data confirming exactly how much protection that partial gravity would actually provide, because no human being has ever lived under Mars-level gravity for any meaningful stretch of time. This is one of the genuinely open questions active space medicine research is still working to answer, using a combination of computer modeling, short-duration parabolic flight experiments that briefly simulate different gravity levels, and continued monitoring of astronauts returning from long-duration missions, none of which perfectly substitutes for the real thing. Some researchers studying this exact question have proposed that there might be a specific minimum threshold of gravity, somewhere between the Moon's weaker pull and Mars's stronger one, below which the body simply can't generate enough mechanical loading through ordinary movement to meaningfully slow bone and muscle loss. Though where exactly that threshold sits and whether Mars's 38% falls above or below it remains an active area of investigation rather than a settled fact. It's a genuinely important open question for the actual feasibility of long-duration human presence on Mars, and one that current research involving everything from centrifuge experiments on Earth to careful analysis of the limited relevant data we do have is still working to answer with real confidence. What we can say with real confidence is this: over a mission lasting many months, the kind of time frame a genuine Mars expedition would require, given how planetary orbits align, an astronaut would almost certainly experience measurable bone density loss, measurable muscle atrophy, and measurable cardiovascular deconditioning. Their heart, no longer needing to work as hard pumping blood against Earth's full gravitational demand, gradually adapting to the reduced workload in ways that would need to be actively, deliberately counteracted through dedicated exercise, the same basic strategy already used aboard orbiting space stations, just calibrated for Mars's specific gravity level rather than true weightlessness. None of this would kill an astronaut on Mars itself. It's a threat that reveals itself later, most dramatically at the moment of returning to a stronger gravitational field, whether that's Earth's full gravity after a Mars mission, or even just the jarring transition of a Mars-based astronaut attempting strenuous activity after months of reduced loading. Astronauts returning from long-duration missions aboard orbiting stations often require weeks of dedicated physical rehabilitation just to safely walk, stand for extended periods, and use the bathroom without assistance. Their bodies having quietly, gradually adapted to an environment no longer demanding what Earth's gravity had always silently required. Astronauts have described this return experience in strikingly consistent terms across different missions and different space agencies. A profound, almost disorienting heaviness to their own limbs. Simple tasks like lifting a cup or turning their head suddenly requiring conscious, deliberate effort in a way they never had before launch. Some have described the sensation as feeling, quite literally, like gravity itself had become a hostile force actively working against them, rather than the invisible, unremarkable background condition it had always been for their entire lives before spaceflight. Even holding a phone up to an ear, or simply keeping their own head upright without the support of a chair, can feel unexpectedly exhausting in the first days after return. A strange, humbling reminder of just how much of what feels effortless is actually being quietly subsidized by muscles and bones your body has, without complaint, kept strong for exactly this purpose your entire life. It typically takes several weeks of careful, medically supervised rehabilitation, gradually reintroducing weight-bearing activity before an astronaut's bones, muscles, and cardiovascular system fully readjust to functioning under Earth's full gravitational demand again, and even then, some degree of bone density loss can persist for months or longer after return. An ongoing area of medical monitoring for returning crew members. A hypothetical Mars mission would likely see a somewhat gentler version of this same readjustment, given the smaller gravitational gap between Mars and Earth compared to the gap between weightlessness and Earth. But the underlying physiological principle, a body quietly, efficiently adapting to whatever gravitational demand it's actually given, and needing time and deliberate effort to adapt back, would remain exactly the same. So let's finally put the complete, honest ranking together, all of it, side by side, exactly the way we promised at the start of tonight's video. Remember the guess I asked you to drop in the comments, cold or lack of air? Here's the actual complete answer, ranked from fastest to slowest, based on everything the real evidence tells us. Fastest and most immediately lethal, by an enormous margin, the mechanical failure of your body's fluids due to Mars's near-vacuum atmospheric pressure, triggering embolism and oxygen deprivation within roughly 10 to 15 seconds of full, unprotected exposure. This isn't close. Nothing else on this list comes anywhere near matching that speed. Second, and only relevant in the specific scenario where cold, rather than pressure, becomes the dominant problem, such as a suit failure that compromises insulation and heating without causing total pressure loss, hypothermia, which could become seriously dangerous within tens of minutes given Mars's brutal average temperatures and dramatic day-to-night swings, though considerably slower than the pressure threat when both are present simultaneously. Third, oxygen deprivation and carbon dioxide toxicity from breathing Mars's actual atmospheric composition directly, relevant primarily in scenarios where pressure and temperature are somehow maintained, but the breathing air itself becomes compromised, unfolding over a period of minutes rather than seconds. Fourth, considerably slower and more cumulative perchlorate exposure through inhaled dust and contaminated water or food, a threat that builds over days, weeks, and months of sustained exposure rather than presenting any immediate danger from brief contact. Fifth, and slowest of all in terms of acute danger, despite its fearsome reputation, radiation exposure. A real and serious long-term cancer risk requiring careful mission planning and habitat shielding, but not a threat that would meaningfully harm an astronaut over the course of days or even several months on the surface. And running alongside all of these, not really a hazard in the traditional sense, but a persistent, ongoing condition demanding active daily management for the entire duration of any stay. The slow, cumulative toll of reduced gravity on bone, muscle, and cardiovascular health, a threat that reveals its true cost only much later, often after returning to a stronger gravitational field entirely. Notice how differently this ranking is organized compared to how most people, myself included, before I actually sat down and worked through the real numbers, would have instinctively guessed it. The threats sound scariest in almost exactly the reverse order of how quickly they'd actually harm you. Radiation, the word that probably makes the most people nervous on first hearing it, sits dead last in terms of acute danger. Pressure, a word that barely registers as a threat at all in most people's mental model of Mars, sits so far ahead of everything else that it's barely fair to call this a ranking at all. More like one overwhelming danger followed by a long tail of considerably slower, more manageable ones. There's a useful general lesson buried in that inversion, one that extends well beyond Mars. Human intuition about danger tends to get calibrated by vividness and familiarity rather than by actual statistical likelihood or speed of onset, which is exactly why people often report more fear of flying than driving, despite driving being, mile for mile, considerably more dangerous by nearly every available measure, simply because plane crashes are rarer, more dramatic, and more heavily covered when they do happen, while car accidents are common enough to fade into unremarkable background noise. The same basic mismatch shows up again and again across completely unrelated fields, from how people rank the danger of different foods to how they judge the risk of different medical procedures, always tending to overweight vivid, dramatic, unfamiliar threats and underweight quiet, familiar, statistically significant ones. Mars's danger ranking follows the exact same underlying pattern. Radiation is vivid, culturally loaded, and immediately evokes decades of dramatic imagery, mushroom clouds, glowing green symbols, science fiction mutants. Atmospheric pressure is invisible, abstract, and something most people have simply never had a reason to think carefully about, right up until the actual numbers get put in front of them. If your original guess was cold, you were closer to being right than you probably realized a few minutes ago. Because cold genuinely does rank as one of the faster, more serious threats, just not the fastest one, and not for the reason most people assume. If you guessed suffocation from lack of oxygen, you were onto something real too, since breathing Mars's actual atmosphere would indeed kill you, just considerably more slowly than the pressure problem that gets you first, in nearly every realistic version of this scenario. And if pressure or ebulism or anything related to your blood's boiling point genuinely crossed your mind before you watched this video, then genuinely, sincerely, well done. Because that's not a common first guess, and it happens to be the correct one. I think what makes this whole ranking genuinely worth building carefully, rather than just listing Mars's dangers in whatever order sounds most dramatic, is what it reveals about the actual shape of danger itself, on Mars and honestly everywhere else too. The things that sound the scariest in the abstract, radiation, toxic soil, a planet-swallowing dust storm, aren't necessarily the things that would actually kill you fastest, or even kill you at all in most realistic scenarios. And the thing that actually would kill you fastest, a basic mismatch between your body's calibration and the outside air pressure, is so unglamorous, so purely mechanical, that it barely registers as a danger at all in most people's imagination before they've thought it through carefully. This isn't really a Mars-specific lesson either. if you stop and think about it. Plenty of genuinely dangerous things in ordinary life on Earth follow this exact same pattern, sounding far less alarming than they actually are, while plenty of things with fearsome reputations turn out to be considerably less dangerous, statistically, than the quiet and glamorous risks most people never think twice about. Real danger, it turns out, doesn't always announce itself with the loudest reputation. Sometimes it's just quietly, patiently, waiting in a number most of us never had a reason to learn, like 600 pascals, doing its work in the 10 seconds before anything more dramatic even gets the chance to start. There's a broader point sitting underneath all of tonight's specific numbers, one that I think is worth carrying with you longer than any individual fact about pressure or perchlorate. Every single day of your life, an entire invisible support system has been quietly keeping you alive, doing work so constant and so reliable that you've never had a single reason to notice it. The right pressure holding your fluids together. The right gas mixture filling your lungs with every breath. A magnetic field and an atmosphere working together to filter out the worst of what space throws at this planet. A gravity strong enough to keep your bones and muscles honestly working without you ever having to think about it every single day since before you could walk. None of this was ever guaranteed. It's the product of a specific, narrow set of planetary conditions, 4.5 billion years of geological and atmospheric history that happened to converge on this one particular rock into something gentle enough to let complex, oxygen-breathing, thin-skinned creatures like us exist at all, let alone build spacecraft capable of reaching a planet where every single one of those conditions fails in its own specific, fascinating way. Think about how many separate, independent systems had to line up correctly, all at once, for this exact moment, you sitting here listening to this sentence to be possible at all. A planet massive enough to hold on to a thick atmosphere, but not so massive that gravity became crushing. A molten core still churning today, generating a magnetic field that's been quietly deflecting solar particles for the entire span of complex life's existence on this planet. An atmosphere with exactly the right composition and thickness to hold a stable temperature and a breathable gas mixture at once. A chemical environment stable enough that thyroid-disrupting compounds like perchlorate never accumulated to dangerous concentrations across Earth's surface the way they have across Mars's. None of it was inevitable. All of it, somehow, happened anyway, on this one particular rock, orbiting this one particular star at exactly the right distance for exactly long enough for something like you to eventually exist and start asking these exact questions about a neighboring planet that never got quite so lucky. Mars isn't hostile because it's uniquely cursed or unusually cruel, as strange as that might sound after everything we've just walked through. It's hostile because it simply lacks the specific, narrow, and genuinely rare combination of features Earth happens to have, features so completely reliable in our own daily lives that most of us go our entire lives without ever consciously appreciating even one of them. Understanding exactly how Mars fails, precisely and specifically, pressure first, then cold, then breathable air, then toxic dust, then radiation, then gravity itself, is really just another way of understanding, with unusual clarity, exactly how much your own ordinary, uneventful day back here on Earth is quietly, invisibly succeeding. If tonight's ranking surprised you, and I genuinely bet it did for at least one item on that list, drop a comment and tell me which part flipped your expectations the hardest. Was it the 10 to 15 second timeline for pressure loss? The fact that radiation, of all things, ranks as one of the slowest, least urgent threats rather than one of the fastest? Or the detail about perchlorate once being used as an actual medical treatment decades before anyone thought to look for it on Mars? I read every single comment, and honestly, this kind of feedback shapes which topics we tackle next more than almost anything else. I'll be honest, when I first started researching this specific video, I expected radiation to end up somewhere near the top of the ranking, simply because that's the reputation it's carried in nearly everything I'd ever read or watched about Mars before sitting down and actually working through the measured numbers myself. Finding out just how far down the list it actually belongs was genuinely one of the more surprising moments in putting this whole script together, and if a topic like this can still surprise someone who spends this much time researching it, I think that says something real about how much our collective intuition about dangerous tends to lag behind the actual evidence. It's a useful reminder to stay a little humble about any strongly held assumption, even one that feels as obvious and well established as radiation is one of the scariest things about Mars, right up until you actually sit down with the real measurements and let them speak for themselves. And if you made it all the way through both halves of tonight's story, and you're the kind of person who wants your sense of extreme and dangerous recalibrated by actual evidence rather than movie logic, subscribe. Because that recalibration is basically the entire point of this channel. Every single video here starts from the same basic premise. The universe is stranger and often differently dangerous than our first instincts assume, and the only way to actually know the difference is to sit down with the real numbers and follow them wherever they honestly lead, even when that means overturning an assumption you walked in with. Until next time, take a slow, deliberate breath, notice the pressure of the air filling your lungs, notice your own gravity-calibrated body holding itself upright without any conscious effort at all. And remember that every single one of those small, unremarkable, completely reliable things is doing more work right now keeping you alive than any single dramatic disaster ever could. Mars will still be there the next time you look up at the night sky, a small, steady, reddish point of light, quietly holding on to its own 600 pascals, its own thin veil of carbon dioxide, its own toxic dust, and its own faint, patchy magnetism, exactly as indifferent to your presence as it's been for 4.5 billion years, and exactly as fascinating for precisely that reason. Somewhere on that small red point of light, dust is drifting across empty plains under a sky too thin to hold on to the day's warmth. Radiation is quietly accumulating in rock that's never known a single living thing to protect. And the whole slow, patient, indifferent process will keep right on happening whether or not anyone from Earth ever actually stands there to notice it. At least for now. Until the day, decades or centuries from now, when someone finally does, carrying with them everything we've walked through tonight, and hopefully a healthy respect for exactly which of Mars's dangers actually deserves their attention first. Built into the suit they wear, the habitat they shelter in, and the honest, evidence-based ranking that made it possible for them to survive long enough to see the sunrise on a planet that was never built to make that easy.